Welcome back to Chemistry Matters, Unit 6, the mole and stoichiometry. In our last video on the Unit 6 playlist, we executed 2 conversion problems and had our students use dimensional analysis. You'll be using this technique a lot as you perform chemical calculations. I mentioned the mole early in the last video, and you heard our teacher reference it near the end of the last segment. So now's a good time to investigate the concept of the mole. What exactly is a mole in chemistry, and why is it such an important concept? The mole is a number, an incredibly large number. It's equal to 6.02 times 10 to the 23rd power. Just as a dozen represents 12 of something, a mole represents 6.02 times 10 to the 23rd of something. For example, if a bottle contains 1 mole of helium gas, you know that it contains 6.02 times 10 to the 23rd helium atoms. What if a bottle contained 0.5 moles of helium? How many helium atoms would be in the bottle? It would contain half a mole, which is 3.01 times 10 to the 23rd atoms. It works exactly like a dozen or a half dozen. So again, the question you might be asking yourself is, why is this important? Well, when dealing with masses of macroscopic substances, objects we can easily see, we typically use units such as grams or kilograms. These units work just fine if we're massing out rocks or dumbbells or just about anything else we can easily weigh. However, if what we're concerned with massing is a hydrogen atom, these units become more cumbersome. Measuring the mass of one hydrogen atom is very difficult, but if we gather together a large number of hydrogen atoms, it becomes much simpler to measure the mass. For example, the mass of a typical hydrogen atom is around 1.66 times 10 to the negative 24 grams. Who wants to be going around doing calculations with numbers that are so ridiculously small? Here's where the mole can become really helpful in chemistry. Measuring the mass of a mole of hydrogen is much easier since a mole is such a huge number. Scientists began using the mole as a unit of measurement back in the 1800s, and they found it to be so useful, the decision was made to name the number of atoms in a mole, 6.02 times 10 to the 23rd, Avogadro's number, in honor of Amedeo Avogadro, a very influential Italian chemist of the 19th century. Avogadro's number became one of the base units of measurement in the SI system in 1971. With that in mind, let's use the mole to count atoms. We'll take a step-by-step approach to learn how it is possible to relate number of atoms, mass, and volume, all by using the concept of the mole. As we learn these steps, keep your eyes open for this graphic organizer, which will appear on screen when we start mole calculations. This graphic organizer will help you organize your thoughts and remember the goal of each problem. This organizer shows the types of calculations we're likely to perform, such as how many atoms are in a mole, what is the mass of a mole of atoms, or what is the volume of a mole of atoms, for example. Now let's go back to our classroom where our students are learning how to use moles to count the number of atoms in a chemical sample.
The mole is the SI unit that measures the amount of matter a substance has and is often abbreviated as MOL in problems and calculations. The mole can be related to the number of particles in a substance or its mass in grams, or it can also be related to the volume of a substance. A mole is simply 6.02 times 10 to the 23rd representative particles. This is another example of an equivalent statement, like we talked about before. 1 mole equals 6.02 times 10 to the 23rd. Representative particles could be atoms, molecules, or formula units. We can convert from moles of a particular substance to representative particles using Avogadro's number. Or we can convert from particles to moles. You just have to know what type of particle you're starting with and what you're having to convert to. You'll get a better understanding of what if we solve a problem together. The first problem is, how many molecules of water are there in 0.360 moles of water? So does this look like a conversion problem?
Yeah, the question gives us moles, and it wants molecules as an answer.
Excellent. So how could we use dimensional analysis to solve this problem?
Well, we have 0.360 moles to start with, so that needs to go into the upper left-hand corner of the conversion chart.
Yes, that's the correct first step. What's next?
Let's see. We need to let the notes guide the conversion, so we need to write the unit moles of water in the lower right.
Exactly. Now, we want this next column to be a conversion factor, right? And remember, conversion factors are just equivalent statements written in fraction form.
We need to convert to molecules, and we have moles. Is there an equivalent statement for those?
A mole is just 6.02 times 10 to the 23rd of something, so I guess that would work for molecules also, right?
Yeah, and molecules, atoms, and formula units are all examples of representative particles we described a minute ago.
That's right. And Avogadro's number over 1 mole would be the correct conversion factor to use for this problem. So let's make sure the units cancel out and that the unit we're solving for is in the upper right-hand corner of the conversion chart.
They do cancel. We have moles of water in the numerator in one step and in the denominator of another. So they cancel, and we're left with molecules of water in the upper right. So all we need to do is multiply everything in the numerator, 0.360 times 6.02 times 10 to the 23rd molecules over 1. So 2.17 times 10 to the 23rd molecules of water are found in 0.360 moles of water.
Great job. Let's try one more conversion problem involving representative particles and moles. This one asks, how many moles of magnesium are there in 1.25 times 10 to the 23rd magnesium atoms? Who wants to get us started on this one?
I'll try. We need to identify what we're given and what we're trying to solve for. Then place what we're given in the upper left-hand corner of a conversion chart. It looks like we're given atoms this time, and the question wants us to convert that to moles. So let's put 1.25 times 10 to the 23rd magnesium atoms in the upper left-hand corner of a conversion chart.
And of course, we have to let the units guide the conversion. So our next step is to write the units in the lower right-hand box, and this time they're magnesium atoms.
And this is the part where we have to turn an equivalent statement into a conversion factor. But I'm not quite sure where to go from here.
Well, I think it's helpful to constantly remind yourself over the course of these problems what it is you're trying to solve for. It will help you if you can reason through it.
Oh, yeah. Well, since we need to convert to moles and we have particles, well, atoms, to begin with, we can use the equivalent statement 1 mole of magnesium equals 6.02 times 10 to the 23rd magnesium atoms. This time, we'll need to put Avogadro's number in the denominator, and we can put 1 mole of magnesium in the numerator.
That's it. Then we can cancel the units of magnesium atoms, and since we have the unit we're trying to solve for, which was moles of magnesium, we just need to do the math, which in this problem is going to be 1.25 times 10 to the 23rd times 1 mole of magnesium. Then divide that by 6.02 times 10 to the 23rd.
We then divide the numerator by the denominator.
And we get 0.208 moles of magnesium.
Great job, everyone. It seems like you have a good grasp on converting from moles to representative particles and vice versa.
Our students just got a great introduction to converting between moles and particles. Notice on your graphic organizer that our students were converting from moles to representative particles and from representative particles back to moles. If you'd like more help with this concept, you can check out our closer look video on converting moles to particles. If you're ready to continue, now we can make the concept of the mole even more useful by connecting the mole to the mass of substances in grams. To do that, though, it will help to get a little more information on how atomic mass is measured. The unit we use when dealing with masses of atoms is called the AMU, and it stands for atomic mass unit. The AMU is based upon the carbon-12 atom, and the creators of the AMU decided that one atomic mass unit equals 1/12 the mass of a carbon atom. You can think of it this way. A typical carbon atom has a mass of 12 AMU. Now take a look at the periodic table where carbon is. You'll notice carbon has 12.011 listed as its atomic mass. If you had a chance to watch the closer look videos from Unit 3, you got to see how these masses are calculated. Practically speaking, the idea that we would ever measure the masses of a small number of atoms is not realistic. So wouldn't it be nice to have a way to tie all of these concepts together in a way that gives us units that are easy to work with, yet at the same time gives us an accurate description of the numbers of each type of atom present? This is where the mole, the number 6.02 times 10 to the 23rd, comes into play. It's essentially a proportionality constant that allows us to create a conversion factor to convert from AMU to grams, or vice versa if we should choose to do so. Scientists have used dimensional analysis to show that the mass of a single carbon atom is 1.99 times 10 to the negative 23rd grams. Again, this is not a very practical measurement because we would never deal with a single atom. But what would be the mass of carbon if we happen to have a mole of carbon atoms? If we multiplied 1.99 times 10 to the negative 23rd grams by Avogadro's number, also known as the mole, which is 6.02 times 10 to the 23rd, we get 11.98 grams of carbon. Does that number for carbon look familiar? Look at your periodic table and the average atomic mass of carbon. The average atomic mass of carbon is 12.01, very close to 11.98. And when we account for all the isotopes of carbon, we find that 1 mole of carbon atoms has a mass of 12.01 grams. Look to the left at boron with an atomic mass of 10.81. So 1 mole of boron atoms has a mass of 10.81 grams. And look at nitrogen on the right. It has an atomic mass of 14.01. So 1 mole of nitrogen has a molar mass of 14.01 grams. The atomic mass of each element also represents the mass of that element in grams if we were to have a mole of atoms of that element. This is known as the molar mass. Molar mass is the mass in grams of a mole of a substance. Molar mass is the same number as the average atomic mass for an element. So to summarize, if we have a mole of atoms of any element, then we would know what the mass would be in grams. We know this by looking up that element's mass on the periodic table. So there are really 2 important pieces of information that we can derive from those masses listed for each element on the periodic table. 1. The average mass of a single atom of that type of element in atomic mass units. And 2. The mass